Welcome everybody to the Distinguished Lecture Series in Computer Science. Today we are extremely thrilled to welcome Eitan Grinspun from Columbia University. Eitan is I think I first met Eitan when he was still a graduate student, or at least I came across his charming paper on thin shells called Charms, somewhere in the SIGGRAPH milieu. But Eitan is one of the few people in computer graphics who really combines first-rate scientific computation and traditional applied mathematics with computer graphics. So he's a Canadian, got his undergrad degree from the University of Toronto, and went to Caltech for a PhD. And then I think after a brief postdoc at NYU, has been a professor at Columbia, where he's been doing amazing things. He has a reputation of getting almost every paper, I think every paper he submits to SIGGRAPH accepted, which is believe me, a big achievement.
Just means I don't try hard enough.
And his work has been recognized with numerous awards, including an NSF Career Award, a Sloan Fellowship, and I think these are all the academic accolades, but what really matters sometimes in computer graphics is screen credits, and he has those as well, just like Robert Britson here. He has had screen credits for his work on The Hobbit, Planet of the Apes, Tintin, and many other movies. And I have to say, he's also been an excellent postdoc supervisor to many of our former PhD students, and so we know that he's really does amazing work. So welcome.
I want to thank you. Can we lower the volume here for just a little bit? I want to thank you for this opportunity because I know a lot of the faculty at UBC, and I have friends who have come from grad school at UBC. And so I have a lot of connections to this institution. As Dinesh mentioned, I have postdocs who have come from this institution. And so it really is a very unique opportunity for me to be able to speak with you today. Is this all right in terms of the volume in the back? Good. So let me dive right in. I'm going to start the story with a prelude. Since I was asked to give a talk to the computer science department, as opposed to, say, a graphic-specific talk, I want to say something deep about computer science so that it sounds like I'm saying something deep about computer science. So I'm going to say that computer science is about structure, all right? And I just took a bunch of snapshots of different aspects of computer science from the internet. You know, spaces of problems and the hardness of problems, diagrams from relational databases, the inside workings of optimizing compilers. And across the themes across all these disciplines of computer science, we're really interested with how components interrelate, how concepts interrelate, how problems relate to each other. So we're fundamentally interested in studying structure and organization. In fact, we often have a course called computer organization. That's the end of my prelude. But in today's talk, I hope that you will see one way in which we can study structure from the perspective of computer graphics. So let's dive in. So we begin our story with a little recap of computer graphics. With modern rendering techniques, we're able to see statues that are somewhere else in the world, and we're able to see them from every vantage point and every lighting and at the level of chisel marks. We're able to make movies that entertain millions, and we're able to see buildings before they've been built, perhaps preventing colossal terrible decisions in terms of spending money. Now, what's common to these particular images is that they're all frozen in time. And like my colleague Robert Bridson and like my former mentor Michael Van de Pan, who I had the pleasure of taking my first ever graphics class from at the University of Toronto, we're interested in motion and depicting the story of motion. So with that, a little history of animation, really almost a one-slide history. Here's the oldest known depiction of motion as far as I've been able to dig up. This is from the 3rd millennium BC. It was on a vase, and it's been unrolled here for your viewing pleasure, and it tells the story of a goat that's jumping up to reach a leaf. Now, since then, we've made a lot of strides in depicting motion, and one of the important strides has been the concept of persistence of vision, and this is what has enabled Disney, for example, to make images that seem like they're coming to life. And of course, we think of some of the original animated movies like Snow White and the Seven Dwarfs. And what's interesting about these animations is the process by which artists go through when they are creating the animations. In fact, Disney did not take professionally trained illustrators who were trained in anatomy, for example, for his work. Rather, he took a newspaper comic artists because they could tell a story in a sequence of frames. And then, together with various of the lead artists at Disney, they went through a series of exercises. And the most classic of those exercises is what I'm showing up here, is the sack of flour exercise. And the idea in the sack of flour exercise is to depict a sack of flour that simultaneously has emotion, has storytelling, has anticipation, and at the same time has a physical sack of flouriness to it, right? So mixing the physics, which makes things believable, with the storytelling. And that's the sort of process that artists have to go through as they tell a story, and that doesn't matter if it's hand animated or if it's animated using a computer. So one natural question that we face when looking at computer animation is, how do we model the qualitative aspects of a physical system? And I'm going to pitch one potential answer to you today, one of many, but one which I happen to like a lot. And the answer is to follow the geometry. And that's what today's story is going to be about. So let me give you an example of that. Here is the solar system, and one of the things we think about when we think about the solar system is the motion of the planets around the sun. And we could model that motion in a variety of ways. We could write down the inverse radius squared law for gravitation, plug it into an ordinary differential equation, discretize that equation, and crank out an answer. But Kepler offered a different view. Kepler's second law said something very beautiful and something very geometric about the orbit of a planet around the sun. Kepler said, if you draw a radius from the sun to the planet and take out your stopwatch and measure some interval of time, then the radius will sweep out a pizza wedge. And if you repeat that exercise at any other point in the orbit, again, picking the same interval of time, you'll get a different pizza wedge, sometimes short and fat, sometimes long and thin, and Kepler's second law says it'll always have the same area. So that tells us something about the motion of a planet around the sun. And in fact, this connection between physics and geometry has been understood and studied for centuries. But what we are starting to scratch the surface of in recent decades is how that connection between physics and geometry factors into aspects of computation. So putting in algorithms and computation into the mix. And in fact, we can trace back some of the things that motivate this all the way back to Newton's Principia. If you take a page out of the Principia, you'll see that Newton actually provided a proof for Kepler's second law. And Newton did it not using the infinitesimal setting of the calculus, but in the discrete setting. You see, Newton said, if we have the sun here, then we can consider a piecewise linear trajectory of the planet. And the dotted lines, maybe I can point here. Does the pointer work? No. And the dotted lines show where the planet would have continued if it did not have the influence of the sun. And then the lines towards the sun say, at equal intervals of time. Newton thought of the sun as executing a series of clock ticks. At equal periods of time, the sun exerts an impulse on the planet which turns its trajectory. And the planet goes in a different direction, and so on and so forth. In fact, here's a modern reproduction of that same page from the Principia, just showing 2 steps of time. And it turns out that a very simple high school geometry argument about moving a point on a triangle parallel to the base keeps the area of the triangle fixed, is sufficient to show that the green and the blue triangles have the same area. In other words, Newton proved Kepler's second law by showing that a sequence of triangles by induction must always have the same area. And we can take this same diagram and relabel it with the variables of a computer algorithm for integrating a physical system forward in time. And we can write down a simple integration rule where Q is the position, P can be thought of as the velocity. We're going to ignore mass for now. And N is the discrete time step, so N plus 1 is the time after N. H is the size of the elapsed time. And F is the forces acting on the system. Now, I want to compare Newton's algorithm, except Newton wrote it as a proof and we're reinterpreting it as an algorithm, to the classic algorithm that we teach at the beginning of a scientific or numerical computing class. On the left, we have explicit Euler. And on the right, we have this geometric algorithm that's born out of Newton's proof. And the only difference between the algorithms is where the force is evaluated. And you might say, this makes me kind of wheezy because I have an n plus 1 on the right-hand side. That's an unknown future time step. I probably have to solve some linear system to get this. But actually, this is a fully explicit system because Qn plus 1 can be evaluated only from known quantities at the previous time step. And then it can be substituted into the second line. So the computational complexity of these algorithms is equal. But their behavior is very different. On the left, we see that if we run explicit Euler with very tiny time steps, 0.0005, over time, the motion of the planet spirals outward until the planet eventually goes off to Alpha Centauri. And we actually use this as an example to show that explicit Euler is not stable. And on the right, we show symplectic Euler, this geometric algorithm, running with time steps that are 100 times bigger. So in principle, it should be far less accurate. Now, I'm not going to say something about its accuracy on a per time step basis. And in fact, it does drift from the correct trajectory, which is the one shown by a dashed ellipse. But in some sense, it remains qualitatively accurate. It's always an elliptical orbit. And the idea or the spirit we're trying to follow is that this is because the geometry is built directly into the algorithm. So we have something we can say, even for coarse or large time steps, the area of the triangles is exactly preserved, not just in the limit of running smaller and smaller time steps. So how does all this relate? How can I start to play with these concepts of geometry, physics, and computation and how they interrelate? One setting in which we can discuss this is the setting of contact. Here I have a simulation of a ribbon being tied into a knot. And I would like to have a simulation that is at the same time respecting the geometry, the physics, and computational principles. In fact, I'd like to start from the premise that if we start with a very principled view of this computation, we can then work towards making it faster. And I'd like to contrast this with another approach that might be, let's make a very practical algorithm that gets the job done, might not be so correct, And then over time, we can make it more correct by saying that, copying the words of Sutter and Alice Andrescu and saying it's far, far easier to make a correct program fast than it is to make a fast program correct. So what does it mean to make a program correct when we're talking about the physics, the geometry, and the computation? Well, in terms of geometry, one thing that we can say is that if we have many layers of material, they should never, ever penetrate through each other. And in fact, actually, one of Robert Bridson's seminal papers laid out this invariance condition that said, guarantee that at every time step, you do not have interpenetrations, and don't finish the time step until that's correct. So that's a very straightforward thing that we can ask for. Another thing we can ask for, again, as in the case that we saw with Kepler's second law, is some sort of correctness in the sense of conserved quantities. If we don't have a source of energy loss or heat transfer or sound in the system, if we're trying to keep all the energy in terms of potential and kinetic energy, then we might expect that when a metal ball is hitting against a metal plate, all of the energy is somehow retained, either in the elastic or in the kinetic energy. So we might want to expect a red line for the energy. And one of the state-of-the-art finite element algorithms for doing these kinds of simulations almost gets that. But when you zoom in, you can see that after one collision, you have some amount of energy loss. This is not energy loss that's been modeled into the physics. This is an artifact of the algorithm. And once you have such an artifact, you can't control it. You don't know how much energy loss you will have depending on the scene that you set up. That's the trouble there. Now, of course, in practice, you do want to have some energy loss. You want to be able to run algorithms with different amounts of dissipation. But again, the premise is that if you can start with something that has these conserved quantities, then you can model your own energy loss, and you can see that the behaviors you're getting, say, for different coefficients of restitution, and here I have time and energy, is a function of the model you've introduced and not an artifact of the algorithm that you have used to solve the problem. So I call this second point physical correctness. And the third point is one that we like to talk about when we discuss distributed systems, computer networking, protocols, and so on and so forth, and that's computational progress. We want to make sure that if the problem is well posed, and if the input to the problem is finite, in a sense that can be made precise, then the computation time will be finite. Finite does not mean it'll take 5 minutes. It could take days, but it will end, and you don't have any questions about the fact that it will end. That's it. Okay, so what are ways in which people have approached computing contact for physical systems? One class of methods is called the penalty approach. If you think of having a ball and having a wall, and the ball's approaching the wall, you can look at the distance between the ball and the wall, and you can set up a kind of energetic potential that penalizes the ball approaching the wall. And I've drawn this potential in blue there, and I've made it quadratic. And so as the ball approaches the wall, some of the kinetic energy is transferred into the quadratic potential. And if the ball doesn't have too much kinetic energy, all of the energy is transferred to the quadratic potential, and then eventually the ball, it's all reversed, and the ball moves away, and the collision is successfully resolved. Now, why have I made the potential quadratic? I've made it quadratic because for a quadratic potential, I know how to pick a stable time step size so that my simulation does not blow up. That's why I've chosen that. The problem with a quadratic potential is that there exists sufficiently fast motions of the ball, that is sufficiently large kinetic energy, such that even after the quadratic potential has absorbed a bunch of the energy, there's still enough energy left over that the ball just tunnels right through the wall. So that violates the geometric criteria that we set up at the beginning. Another approach that we could use is an impulse-based method. An impulse-based method just says, basically run your simulation until the instant at which a collision is about to occur. Ball's approaching the wall. Stop the simulation at this instant. Compute some sort of impulse that reflects the motion of the ball, and then have the ball continue along this new direction. This is very different than the soft penalty approach. It's instantaneous and impulsive. The problem with an impulse method is that there actually exist situations in which an impulse cannot resolve a collision. For example, if I have this cubic-shaped wall and I have a ball approach it, it actually ends up approaching the wall tangentially, at which point there is no valid impulse. There's no impulse that preserves energy that also allows the ball not to penetrate the wall. So you cannot make progress past this point. So this picture kind of summarizes what we've seen so far, which is that penalty methods are not safe in the geometric sense, and impulsive methods do not guarantee progress. So people have looked at ways of resolving this. In Robert Bridson's thesis work, for example, he said we can take the best of impulsive methods and penalty methods, and in order to guarantee progress, whenever we've looped a few times and we can't resolve everything, we're going to use a geometric method, which does not have any pretense of being fully physically correct. There's no such claim being made. The claim is that it will get the job done in the sense that things won't collide and we can move forward in time. We may lose some energy, but that's life. So these geometric models, in essence, sacrifice correctness. And so we have this kind of feature chart here that basically says existing methods seem to lose one of the properties that we desire in this interplay between computation, geometry, and physics. So we were interested in seeing if there exists a method that does satisfy all of these desiderata. And so we make the observation that instead of having a potential that is just quadratically growing, if you have a potential that blows up to infinity, then no matter how much kinetic energy you have, it will all be transferred into the potential energy. And then the ball will go back and all the potential will be transferred back to the kinetic energy. But the problem with a potential that blows up to infinity is that the second derivative of the potential also goes to infinity, and the second derivative controls what is a stable time step for the simulation. And so it turns out that it's very hard in advance to analyze your problem and make a prediction for what time step would be stable. So you have this problem that you cannot easily run such a system. So we need some way of adapting the time step, and ideally some way of adapting the time step that doesn't break all the other good properties like good energy behavior that we're looking for. So this made a case for perhaps trying something asynchronous. And here what I mean by asynchronous is that I'm going to have different parts of the simulation advance at different speeds. Where there's a lot of complicated collisions happening, we might advance the simulation in very small time steps. And where the going is pretty easy, we take nice large time steps. And here's what the snapshot of such a simulation might look like. The x-axis is time, and the y-axis is a percentile graph. And what we're showing is, on the top you can see the heat map, where red means really tiny time steps, and blue means very large time steps. And you can see that only a very small fraction of the simulation needs to invest in really small steps of time, and the rest can run at pretty large time steps. So how do we kind of realize this? How do we make that transformation? So we actually go back and recall Newton's proof. And we interpret it, again, with this notion of a clock ticking and applying an impulse like the sun was doing on the planet. So if I have a ball and I have a gravitational force, I can think of having a clock, and every time the clock ticks, the gravitational force exerts some impulse on the ball, and so on and so forth. And if I have a gravitational force and a wind force, a synchronous method would say that at every time step, they both exert a force on the ball. But what an asynchronous method will do is it will give two different clocks to the two forces. And so whenever the gravitational clock ticks, there will be a force due to gravity, and whenever the wind clock ticks, there will be a force due to wind, and in between, the ball will continue in a straight line. And so here comes the central idea for how we can mix this asynchronous view with this divergent potential that we want to make present in order to ensure that a ball does not tunnel through the wall. The idea is that the idea is to discretize a divergent potential by an infinite sum of quadratic potentials. Let me show you this in pictures. I can start with a single quadratic potential, and I can add to it a steeper quadratic potential over a narrower region, and a steeper one, and so on and so forth. This is now an infinite sum, and so the sum blows up. I'm discretizing this infinite potential, but it has the particular property that any one of the quadratic potentials has a constant second derivative. So any one of the quadratic potentials can execute at a known clock rate that is safe. I don't have to guess ahead of time what clock rate might be safe. So I have all of these quadratic potentials, and I assign a different asynchronous clock to each potential. So now we have a problem, and this is where we start to see the interplay between geometry, physics, and computation. I just told you that in order to ensure safety, you need a divergent potential. And in order to get a divergent potential, you need an infinite sum of quadratic potentials, which means you have an infinite sum of clocks ticking, each ticking faster than the next, which means that you have an infinite number of clock ticks that your computer has to resolve, even in finite time. And that sounds like something that's not going to make a lot of progress. But I want you to realize that each steeper quadratic function starts off later or closer to the wall than the shallower ones. So let me show you that picture in terms of a ball and a wall. When the ball is far away from the wall, the ball is in a flat region. It's not touching any potentials. So none of the clocks are actually exerting an impulse on the ball. In other words, we have an infinite number of clocks ticking at any interval of time, but they're all no-ops. They exert a zero impulse on the ball. The first time we see an impulse is when the clock enters this first layer. At that point, only the first quadratic potential is not doing no-ops. It's exerting a force at regular intervals. But all the other potentials are operating closer to the wall. So while in principle they're all ticking, they're still all doing no-ops. So every time the ball approaches the wall, more and more of the nested potentials are active. But at any given point, as long as the ball is not touching the wall, only a finite number of potentials is active. And that's the key insight. Because it means that even though we have an infinite number of clocks ticking at any given time, only a finite number of clocks are actually doing work. The rest are doing no-ops. And so we've transformed this from a kind of conundrum about an infinite number of clocks into just the problem of culling away no-ops in our code, or culling away those operations that are not doing anything. And there are a variety of ways in which we can cull. One thing that I will say, just for Uri Asher's sake, let's say that, is that you cannot change the phase of the clock ticks. One of the things that we would have liked to do is just say, forget about all the clocks. Every time you pass into a new region, just create a clock for that region. Then you break all this nice symplectic structure. It has to be that these clocks have existed for all of time, and their phase has always gone. So you're really always simulating, your program is accurately simulating the effect of an infinite number of clocks. It is just smart about culling away the ones that are not doing any work. So there are a variety of ways in which you could implement this. One of them is you could use standard collision detection data structures. Another way is to look to computational geometry, where people have used these things called kinetic data structures, which are data structures that always maintain a proof about your system as your system evolves in time. So you could have a proof that your ball is further away from the wall than a certain amount, and that proof enables you to cull away certain clock ticks. And another way you could do it is you could guess. You could say, I guess that a certain number of clocks are active and all the rest are not. Then simulate forward for some period of time, and then retroactively look back at your trajectory and check, because it's easier to look backwards in time, check if your trajectory went closer to the wall than the distance that you had assumed. And if so, you have to roll back your simulation and try again. So there's a variety of ways, and we've looked and played with all of those. And they all have some advantages. I want to recap how we fulfilled these three things. So we got geometric safety by using an energetic potential that blows up, because that means no matter how fast the ball is moving, all of its kinetic energy can be absorbed by this potential. We got progress by saying this requires an infinite number of clocks, but only a finite number are actually doing useful work. And then we put those two things in the context of a geometric integrator of the kind that, in a sense, Newton envisioned in order to get this good energy behavior. Here's the kind of results you can get from such a system. Here, we're draping cloth over a bed of needles. And each needle is made from 4 nearly degenerate triangles. Their aspect ratio is almost infinite. This is considered very hard in collision detection and collision response. And then we pull one of the pieces of clothing from under the other. And this is a test for whether the system introduces any accidental friction. We're not modeling any friction here. If the algorithm accidentally added friction, when you have something very sharp against one of the cloths and you move the other, you'd see some dragging. And you don't, so we're really separating out the modes. Here's a different test. This one's actually inspired by Robert Ridson's PhD thesis. It's called the twister example. And so we have a piece of cloth and a cylinder going through it, and the cylinder is just turning and turning, and we can go forever. The program can go forever. Or for any finite amount of energy you give the cylinder, it'll run and it will terminate. So an algorithm like the one I'm showing here guarantees these three things, but it doesn't guarantee that it'll do them fast, just finitely. And the first time we published this algorithm, I think it was at least 100 times slower than what Robert had done maybe 7 years earlier for those problems that both algorithms could solve. But what this algorithm does offer is that in the case where all the other algorithms just can't do the simulation, this one will chug away just the same as any other. Since then, we've been able to get about 100 times speed up over the original algorithm. So it's coming along. But its main strength is in the fact that you don't have to tune parameters. See, as I was talking with Robert over lunch, there's two kinds of things that you can measure when you're playing with a simulation. You have to set, the human has to set some parameters, then you run the simulation, then you check if it's okay, and then you loop again. And so on the one hand, you have computer time, on the other hand, you have user time. So if you have an algorithm that takes very little computer time but keeps drawing the user back in because you don't like the results or things are going through each other, that's a very different flavor of an algorithm than one where you set it up once, fire, and forget. And just as this other red line here is the line from this algorithm. Okay, I want to switch gears or tell you about another collision problem, but now I want to switch from talking about this interaction between computation, geometry, and physics and say, what if you have several different things that you require from your geometry? Not just, say, conservation of areas from the triangles, but multiple things. So here's work by Danny Kaufman and Brennan Smith. Actually, this work began when Danny was here with Dinesh at UBC and has been carried on since then. And it just says, let's look at simultaneous collisions of a bunch of balls. So for example, if I have a red ball approaching the other two and it collides, well, you can expect this ricochet effect. We call it Newton's cradle. And the other ball breaks away. Now, I call this breakaway because the green and the blue balls were initially at 0 relative velocity to each other. But because of something that had nothing to do with their friendship, just another accidental collision coming up at them, they had to part ways. So we call it breakaway. That's called Newton's cradle. Another model problem that's useful is Bernoulli's problem. And Bernoulli's problem is set up such that you have a spatial symmetry. So you have a ball that's coming and hitting the other two, and there's this reflective line of symmetry. And so the natural thing you expect is that an algorithm does not, of its own accord, break this symmetry. You might want to model the symmetry breaking, but then you would want to do this in whatever way reflects your particular physical system. Of course, you want energy conservation, or you want to explicitly model dissipation of energy. You want momentum conservation. And you also want what's called the no Velcro condition, or one-sidedness, which says that collision forces should push things, but they shouldn't pull. Unless you put Velcro on your balls, they don't pull each other. So these properties are interesting not just for billiard balls, but also for rigid bodies. For example, it turns out that you can't model rolling if you don't have breakaway. And if you don't have symmetry, you have funny bounces of your rigid bodies. And if you don't have kinetic energy, you get really funny bounces. So they don't apply just to billiard balls, but to lots of cases of rigid bodies. And so we call these, the 5 fundamental properties, or 5 fundamental requirements from a geometric perspective of rigid bodies. And these are the co-authors of this paper. I'm not going to step through this paper in as much detail as the previous one. Instead, what I'm going to say is that we looked at several classes of methods that exist. Gauss-Seidel methods, Jacobi methods, linear complementarity problems. And we looked at 3 of the properties that were important to us: symmetry, kinetic energy, and breakaway. The other 2 properties are satisfied by all the algorithms, so they were kind of easy. But we found a nice diagonal that suggested something is going on. There seems to be some sacrifice of one of the properties for the other 2. That's what I mean by the structural view of these systems. And so we analyzed each of these algorithms and asked, what's ruining things? Well, if you have an algorithm that introduces an order dependency where there isn't one, for example, if you have Bernoulli's algorithm where you should have symmetry, but you process one of the collisions before the other, you introduce an ordering where there isn't one. Another property is that these algorithms implement a reflection. And this is more technical, I won't get into that. And another is the property that these algorithms may apply an impulse even when objects are not approaching each other. Not because they're designed that way, but because it's an artifact of what happens when you have simultaneous collisions. So we looked at these algorithmic properties and noticed that they match up with the successful and the successes and failures of the desiderata we had. And so we aligned these tables and essentially posed that each of the properties we need from a geometric perspective corresponds to some requirement on the computer algorithm that implements them. And if you take all these together, you can derive formally a computer algorithm that will respect all of these properties. So now, for example, if you ever wanted to drop 2 bunnies that had perfectly rotational 180-degree symmetry, then you could do so, and you could watch them always maintain that symmetry no matter how long you ran the simulation. And if you wanted to drop many bunnies and control the coefficient of restitution, then you could model any sort of energetic behavior you want. Now we said, let's test this on some real-world examples. And there are these beautiful experiments that were done in the lab of Harry Sweeney. And basically, there's many lead ball bearings in an aquarium. And the aquarium is vibrated with a certain frequency and a certain amplitude. And seemingly of their own accord, these ball bearings start to bounce in a beautiful pattern. This is our simulation. And here's a top view of the simulation and photographs from the experiment of Mello, who was in Harry Sweeney's lab at the time. Now you can take the same setup, and the only thing you modify is the frequency and amplitude. And you now run at a different frequency and amplitude, and you get a different pattern. Now when we did these tests on our algorithms, we use the coefficient of restitution reported in the paper, and the radius of the balls reported in the paper, and the frequency and amplitude in the paper. So we did not tune any parameters in order to get these patterns. And in fact, if you talk to a physicist, they might tell you, well, guys, that's kind of trivial because these patterns are really dominated by the geometry of the setup. Well, but that's the point. The point is, if you approach simulation from the perspective of following the geometry or respecting the geometry, then certain kinds of physical problems, those that are dominated by the geometric effects of the system, are very easily captured without, say, very sophisticated or very high-order simulations. So this is pretty cool. We said we just identify some structures that we want to work with, and then we reproduce these structures in a computer algorithm, and then we just show off cool results with bouncing bunnies. So we said this is a great research agenda. Why don't we try to identify all the interesting structures, carry them all over into some grand master discrete algorithm, and then be done with our research forever and just sit back and enjoy ourselves. Did I lose a slide? So the question is it always possible to respect all of the geometry? So we thought so, we hoped so, and we looked at Laplacians. So the Laplace equation appears in every aspect of computer graphics, from denoising a mesh to parametrizing to mesh editing to smoothing. It appears in visualization and simulation. Of course, it appears in engineering applications. And if you open up a standard functional analysis textbook, you'll see that the Laplacian enjoys a bunch of properties that define it. The Laplacian is symmetric. Well, we could talk about it in the sense of adjoints and function spaces and inner products, or we can just say that in the discrete world, the matrix representing a Laplacian should be symmetric. The Laplacian is local. It's a differential operator. So if I modify the function value far away, it doesn't change the second derivative of the function here. The Laplacian is linear in the sense that if I have any linear function on the plane, it's in the kernel or null space of the Laplacian. The Laplacian is positive semi-definite in the sense that we can write a corresponding minimization principle that we can solve instead of Laplace's equation. And the Laplacian satisfies the maximum principle, which basically means if you solve Laplace's equation on some domain, the maximum value of the function you get always lies on the boundary. All right? Another way of saying that is if you have some piece of metal and you apply heat sources only on the boundary, then measure the temperature everywhere. The maximum temperature is always on the boundary. So we looked at various ways in which people have discretized the Laplacian in the literature. This is not only the graphics literature, but finite elements, the broader literature. And the various types of formulations can correspond to these rows that are shown here. And these properties of symmetry, locality, linear precision, and positivity are shown by the columns. The rows are the methods, and the properties are the columns. And this seems to be, again, there's a theme of diagonals here, of missing features, right? But unfortunately, in this case, we were able to prove a no free lunch theorem that says that if you start with a general triangle mesh, you cannot write down a discrete Laplace operator that satisfies all four properties. All right? So you just cannot get a perfect Laplacian in the discrete setting, even though it exists and is perfectly defined as one object in the smooth setting. We can also characterize that there's a subclass of meshes called regular meshes, which are generalizations of Delaunay triangulations. They're a class of weighted Delaunay triangulations, for which you can write down a perfect Laplacian. So the lesson here is that each application requires that we ask for the relevant geometric structure, because if we can't come up with one Laplace operator that's going to satisfy you and you and you, then we need to ask what properties are important for the application that you're pursuing. So in general, when we pursue our research, we start with a physical system, and we ask what property is important for that system. And we were interested in simulating Twizzlers, or generally simulating anything that's thin and flexible and can bend and twist and potentially stretch. And these things appear over all spatial scales. And there's a lot that can be said about elastic rods. And in fact, one of the first people that really spelled out what can be said in graphics was Dinesh. And our work was heavily inspired by what he did. Here, I'm going to simplify what can be said to kind of the minimal structure that needs to be preserved as we go to the discrete setting. And that is the notion that in order to describe the position of an elastic rod, it is not sufficient to specify a curve. Because I can have this curve or this one, and they occupy the same position, but believe me, it's actually hard work to twist this. So there's more going on than just the position of the curve. There is the orientation of the cross-section, which can change. And the right mathematical object for that is a framed curve. It's a curve with a knowledge of how the cross-section is oriented at every point. And the right question that we need to ask is, when is such a framed curve most relaxed? If I twist this and I let it go, it untwists. What defines that most relaxed state? And that notion is given by parallel transport of a frame along a curve. It's the motion of a frame along a curve that keeps the frame adapted to the curve while twisting as little as possible. In other words, the minimal amount of rotation required to keep you adapted. I'm not going to say more about this. We've already gone into technical details in the previous sections. What I'm just going to say is, in general, these discrete differential geometry type talks, they summarize some structure in the smooth setting, and then they say what needs to be carried over to the discrete setting, and then we transition, and we define an equivalent operation, in this case discrete parallel transport on discrete framed curves. That's the basic idea. And we can summarize the requirements for it very simply. I want to switch over from this propaganda about the philosophy to some of the ways that we've started to apply it both in entertainment and outside of entertainment. So really moving on to this part of the talk that said computational, Hollywood physics is a computational science. So let's start with the Hollywood physics. The studio Weta Digital took this elastic rods code and put it through a little obstacle course. And we needed to do some challenging work on dealing with contact between elastic rods, and that took some time. And so since then, it's been used most recently in The Hobbit.
So this is your purpose, to enter the mountain.
All of it.
There are some who do not be wise.
The dark power has found a way back into the world.
And by pure coincidence, around the same time, we were approached by Sunil Hadap at Adobe, who said, I want a better paintbrush for Adobe. And so we said to him, well, we have a bristle. We have a single bristle. Let's work together. So we took the elastic rods code, and Sunil basically coded up his own version of it. And now it runs in real time in Photoshop since Photoshop version 5.5, I think. And you can pull up the different brush parameters, and you can adjust the number of bristles, or the length of the bristles, or their thickness, or their stiffness. And based on doing this, you can get fundamentally different behaviors. If I make it very stiff and short, I can get this kind of behavior, or I can get the splaying of the bristles. And this should be contrasted against the kind of brushes that existed before, which were not physical. And they basically worked like this, by putting down some repeated pattern. Now, this work on the elastic rods was a collaboration with a physicist, a mechanician, formerly known as Basile Doli, who was very interested in studying knots. And so he was using our code to study knots, and he made the observation that, there's been a connection between elastic rods and viscous threads of liquid. You see, if you drop some honey on your scone, it looks like it's coiling like a rope. So we said, okay, maybe we can exploit this connection. And this connection has a lot of implications in industry. 1/3 of all textiles produced in the world are non-woven textiles, meaning they're produced by taking some molten polymer inside a spinning drum with some holes in the drum, and then the polymer spews out of these holes and hardens as it spews out, and so you get a lot of nice formation of threads transforming into rods, or liquid transforming into elastic solid, as well as contacting together. And that's found in all of these different materials. And there's been beautiful work done by Shiu Wester and Lister and also by Stephen Morris on studying these systems from a very basic geometric perspective. Here's an experiment done in the lab in which honey is poured onto a moving belt. And just by holding the tip still from where the honey is falling and just altering the speed of the belt, you can get a variety of different viscous sewing machine patterns. And when I saw this, I said, this is fantastic, because now when I decorate cupcakes, I don't have to move my hand. I just have to drop it from a certain height. But people tell me that it can be used for stretchable electronics or other settings in which you want to control the pattern that's deposited. So we took the elastic rods code and we used what's called the Rayleigh analogy, which says that if you can simulate an elastic material which has stress is proportional to strain, then you can easily simulate a viscous material which has stress is proportional to strain rate. You just need to add a model for surface tension, but basically the code remains the same. And here's a comparison of the patterns obtained by the simulation and the numerical simulation and the experimental simulation. And here's the mandatory deposition of a viscous thread on a bunny. Now, the history of the relation between a coiling rope and coiling honey dates back to the late 1950s, and where this coiling was observed. And so after we worked on this deposition of a viscous thread, we went kind of back to the beginning and said, if we're depositing a viscous thread on a moving belt, which was something experimentalists had already done, and we were just reproducing on the computer, can we go beyond that and go to something experimentalists have not looked at yet? And so we teamed up with Professor Pedro Reis in the mechanics and civil engineering departments at MIT, who was interested in studying the deposition of cables on a moving platform. And this has applications. For example, in World War II, one of the secrets to winning the war was having an oil pipeline that could rapidly transport oil. And this was done by taking steel tubes and making very long steel tubes. In fact, they're so long that they effectively became flexible just because of the length at which we're talking about. And coiling them in huge spools, and then being able to deposit those cables on the ocean floor. Now, these cables are being deposited very deep on the ocean floor. You don't necessarily have a way of seeing what's going on down there, and you want to make sure that you deposit just the right rate. If you go too fast, the cable is straight, and any shifting of the earth snaps it. That's bad. If you go too slow, you just waste a lot of cable, or you get nodding, and if it's an internet communication cable, you can get interference or other things that are undesirable. At the other end of the scale, when you're making stretchable electronics or other material engineering applications, you care about deposition of carbon nanotubes in serpentine form. And you want this to be a passive sort of behavior. You don't want a tiny little print head that moves back and forth. So you want to model for how fast should you move the substrate to get this pattern. So Pedro's approach to this is to say these problems, thank goodness, are dominated by geometry. And if they're dominated by geometry, then it doesn't matter if you're interested in ultimately applying them at a microscale or nanoscale or at a megascale. You can study them at the desktop scale. Because the particular material you're using, whether it's an elastic, whether it's a mouse cable, or whether it's a steel cable, the material law won't matter as much as the geometry of the setup. So Pedro studies these by building a contraption like this one, where you have a deposition of an elastic rod on a moving substrate, and you can just control the speed of the belt. And we study it with our simulation code. And again, you can draw a phase diagram that says for different speeds of the belt, you get different patterns that form, just like for the case of the honey. Now, one of the interesting things that came out of this is that Pedro realized he had to start building, manufacturing his own cables. And this insight came directly out of playing with the simulations. At first, Pedro was purchasing pre-made cable. And he was dropping the spaghetti on a table, not even moving the belt. And he was seeing this really interesting effect, which is that as he dropped the spaghetti, it coiled in one direction for a while. And then once in a while, out of its own volition, it switched and started coiling in the other direction. And when we tried to reproduce this on the computer, we did not see that. Our spaghetti always coiled in one direction. And we started comparing Young's modulus and thickness of the cable and friction and gravity and this and that. And we could not get the inversion of the coiling direction. And we asked Pedro, is there something that we're not seeing? And eventually he said, no, we should be covering everything. And the student went off to do more important things at a film studio. And then we have this beautiful email going from New Zealand to Boston that says, Pedro, by any chance, are you storing the cable in a spool of such and such diameter? I really should put a slide with the email. Because he had a bewildered response that said, I just went and measured the diameter of a spool, and you guessed it within 2%. Okay? Which suggested that the diameter must be affecting things. And in fact, what the student had done is the student had said, let me give the cable some natural curvature. So let me pretend it's been stored on a spool for a long time. And just by playing with the natural curvature, the student was able, this is Junsuk Ju, he was able to match to the video that Pedro had sent us for how often the cable inverts. So this was the dominant parameter. And this was very illustrative for us because it really showed a complement between simulation and experiments. When you're doing an experiment in the lab, what's nice is you have all of physics at your disposition. What's hard is you have to control what physics to factor away. In the simulation, it's exactly the opposite. You start with an empty program. It has no physics. And what's hard is to figure out what physics to insert. So by default, our simulation was running with a rod that had no imperfections. It was perfectly straight. But by purchasing a cable from the market, and of course having it shipped on a spool, by default, Pedro was using a cable that had natural curvature. Since then, we've done a lot of validation, a lot of comparisons between simulation and experiment, and we're writing up a paper on that. I want to wrap up today's talk with this one last direction, just for a couple minutes. And it's really inspired by this observation that some of these geometric algorithms really capture the qualitative behavior, so they can run in real time in Photoshop, or they can run offline in a film animation. And I want to say that interaction is essential for design processes. If I show you one of these puzzles that you have to pull apart, and I tell you, please, Ella, just think really hard about this puzzle. Just think about it. Don't touch it, just think. And when you're ready, you can grab it and pull it apart. Okay? But I will tell Chen, Chen, you can play with it and just fiddle with it. All right? Who is going to take it apart faster? The person who just thinks about it as long as they want and then picks it up, or the person who fiddles with it?
Don't answer.
So somehow interaction is really important for understanding the space of a physical system, for understanding what's going on. And so we thought of this in the context of, say, clothing design. In clothing design, it's a really hard problem because you envision some sort of clothing, and then how do you actually make the clothing? You have to cut out flat pieces from a flat textile, stitch them together, put them on a mannequin, and see if you like it. And if you don't like it, you have to figure out how to alter it and start again. So this is a very labor-intensive process. In fact, the process of prototyping clothing on its own costs $10 billion a year in the world, according to Optitex, one of the companies that designs garment CAD software. And if you're trying to design on an armadillo, it's even harder because there's a tail and because you've never done it before. So anytime you want to make radically new designs, it's hard to build intuition. So the idea is that if you can marry simulation as an integral, interactive part of a design process, you can make this loop between trial and error as invisible as possible and really allow for intuition building during the design process. So that as I manipulate the garment, I get a much better sense for how the design changes. So this was work by Nobuyuki Umetani and Danny Kaufman, who also designed this beautiful garb for the armadillo. And Takeo Igarashi actually created the garb, and here it is. And Danny worked with a company called Thunder Lily to transfer this technology into the real world. And Thunder Lily is a company that solicits designs from anyone who wants to be a designer. And they make the designs possible and they make them real. And one of the ways they can do this and do this cost effectively is by using this software to create the designs. And just a couple weeks ago, Thunder Lily was written up in Phoenix Fashion Week for one of the designs created in part using these tools. Now, I myself am a designer, and soon you will be able to buy your first ever Grinspun. It'll come in this striking pattern, so keep that in mind. So I want to sum up for today by saying that, as graphics people, we get to play with armadillos, we get to play with bunnies, and we get to do all kinds of things to bunnies. But there is some interesting ways in which we can do all this. We can think about algorithmic structure underlying these processes, and so really put it in this computer science sort of flavor. And here it is, the garment. You too can have it, and I thank you very much.
So we have plenty of time for questions.
Nice costume.
Is there a faster way to go from a particular phenomena that you see, like such as this coiling, other than just taking your simulation, dialing through all the parameters, and kind of comparing it?
So, ideally, so the answer is yes. So the answer is that there has to be a faster way because there exist these phase diagrams, which basically, show that if you have say, speed of the belt, right, and height from which the honey is dropped, then you get these very clear delineations between when it's coiling and when it's meandering and so forth. So if you have one of these phase diagrams, you should be able to just read off where you are and at least predict the type of pattern and probably have a reduced model for. And in fact, the reason that mechanicians are so interested in building these phase diagrams is because in their world, this is a way of creating understanding. You give an engineer in the field this phase diagram, and they can very quickly identify the ballpark for where they should be operating. Now, I don't have a recipe for a faster way of creating the phase diagram. I think it would be interesting to try some model reduction techniques within each phase. And that's not something I've looked at. But certainly, once you have the phase diagram, you should be able to create animations or simulations or predictions very quickly from it.
Okay. So I had a question about your impact model discussion. So you still have this zone where something non-physical happens. So if you have, often in some of these situations, you actually care about what's happening at very low length scales. And so if I understand correctly, in those simulations, if you had something approaching tangentially that would actually miss, it could come under the influence of this zone and sort of be kicked out, even though it would actually have missed.
Right.
Is there any potential for another? Are there hints of another theory that doesn't involve the notion of a zone?
Yeah. So first, just to be clear, you're referring to the first paper on the knot tying, not to the billiard ball sort of paper.
I'm thinking more of rigid body collisions. So.
Okay. So in the rigid body paper, in that second paper that I showed with the billiard balls, in our case, we were assuming a finite size clock, and any trajectories that were going to overlap during that interval of time would be handled as simultaneous. However, any trajectories that are not overlapping, in other words, where the balls are nearly grazing but not overlapping, would not be treated simultaneously in that paper. So in that work, you could actually make the clock arbitrarily small. It would be more costly, depending on the velocities in your system and the length scales at which you cared about. But if you think about it, the rigid body limit, in some sense, doesn't really make sense, at least to me, in the limit of infinitely small length scales. Because at some point, when you care about really small length scales, any material has some, perhaps very stiff elasticity to it. So at some point, you want to capture that behavior. So there's a contradiction there, Dinesh?
So, first of all, I really love the fact that you are always trying to get correctness into graphics and dispelling the myths that graphics people are cheating all the time.
Although I did not dispel the myth that we use bunnies and armadillos.
But so when we define correctness in terms of getting the right answer, which respects something, but there are a couple of other ways in which you can think of correctness. One is to get the answer at the right time, which is the kind of the real-time constraint. And more recently, getting the answer within a certain budget, for example, on a mobile phone or something like that. What do you think, how would you proceed to try to get the same type of formal approach into...
And let me add to your... So the question is about correctness and essentially why pick those specific desiderata? What about energy consumption? Okay, so that's another metric that matters. What about time, real time? Or let me throw out Tamara's point. Might be what about perception? Is it perceptually correct, right? And maybe that's different than just physical correctness. I think those are all really important. And what I'd love to see is, as much as possible, works in graphics and in other disciplines really setting these kinds of standards. And then saying, do we hit these standards or do we not hit the standards? I think I've been for about a year thinking it would be really cool to do papers on energy-aware geometry processing or energy-aware physical simulation. So maybe your metric is not the speed at which you complete. Maybe it's how much electricity you consume. Because the fact is that right now, the size of our data centers or compute rooms are often limited by our ability to cool them. And so I may not be able to run certain simulations or certain large data sets simply because it's going to overheat all my computers, right? So maybe energy aware, or as you pointed out, some real-time requirements. Now, I would debate the fact that, It's tricky it may be hard to put real time and some of the other things in the same bucket. And it depends when in history you're talking about it, right? So the size of the problem that you can solve in real time subject to other constraints will obviously evolve over time. That said, it would be very interesting to say, give me a solution in this time window that has these properties. So even if you couldn't solve to convergence, you still preserve symmetry, or you still guarantee no collisions. If you have to stop at a specific time, guarantee no collisions by some geometric approach. I think there's some interesting questions to ask there.
More questions?
I'm curious about your Laplacian work. So fun to have a no-can-do theorem. But I didn't really, not being in the field, I didn't understand totally the implications in the sense that, sure, there's a subset, these generalized Delaney triangulations. For all I know, for all practical purposes, that does most of the work for you. So, there's the technical definition of what's doable, but I didn't understand if that actually makes it undoable in practice, or there's lots of stuff that isn't covered by general.
In practice, if you survey geometry processing papers, they have failure cases. And if you look at geometry processing papers that rely on solving Laplace's equation, for example, they will have some failure cases of inverted elements, right? And parametrizations that are not parametrizations. Or other such things. Or you'll have mesh smoothing that blows up in certain cases. If you say, well, no problem, all I have to do is do some weighted Delaunay retriangulation and then I'm okay, then you have the problem that sometimes that can be very difficult to do for some domains or for some geometries. So the no free lunch is really just saying that you will encounter difficulty one way or the other. And it really puts a framework around the papers that have been published today in terms of which battle they try to choose. Where is the Achilles heel? It says it has to be somewhere, either in the remeshing or in one of the properties. Now, that said, it also offers a bit of a recipe because depending on the type of application that you're pursuing, it's perfectly possible that one of those properties is less important than the others. Okay? If you're doing parametrization, let me give you an example. If you're doing parametrization, the goal of parametrization is to take, Ella Scheffer had one of the seminal works on parametrization, angle-based flattening. The goal there is that if you have a triangle mesh, for example, in 3D, you want to find the best fit triangle mesh in 2D. Because in 2D, you can put an image on it, and then you can map it, and you can get your beautiful graphics. And you want it to have as low distortion as possible, and so forth. So one thing that you might require, a common sense thing, is that if your triangle mesh is already flat to begin with, why would you ever want to parameterize a flat triangle mesh? You wouldn't, but it's a sanity condition. If your triangle mesh is already flat, you should have zero distortion when you parameterize it. That is exactly the linear precision requirement that linear functions vanish in the kernel. If you do a parametrization, you might want the fact that any point on the plane maps to exactly one point on the surface, not to 2 points. So you don't have inversions or foldovers in your parametrization. That is exactly the positivity requirement that I put up there. So for parametrization, you don't want to sacrifice those two things. Now, maybe you're okay with sacrificing locality. Locality says something about the sparsity structure of your matrix. So maybe you say, I'll just use a more expensive method in order to guarantee those things. In other applications, you may sacrifice something else. So it does tell you, okay, be really aware of what you're willing to sacrifice and what you aren't, because you can find operators that will give you some but not the other properties.
I'll just ask the last one about, you haven't talked at all about scalability of these methods, and so how they parallelize, because in today's world it's fine to have a numerical algorithm, but you want one that runs on your giant cluster and to either produce results really quickly or to scale really well. And so does what you are there any direct impacts of some of the ideas
Yeah.
that you've presented on in that direction?
So the question is about scalability, and basically, in today's world, it's not enough to just get an algorithm that runs fast on a single thread or even on a single computer. If you want to solve big problems, you need to have something that scales to multiple threads, either shared memory or distributed. This is an extremely important problem. It's also a problem that, ironically, even though when I was at the University of Toronto, not only I took your graphics class, but I also did some research in distributed and parallelizing, optimizing compilers. But somehow since then I drifted away from that. And ironically, it's only in the past year or two that I really came back to really hitting me hard that this is really important. So one of the ways we got speed up for the asynchronous contact mechanics in the later work is by realizing that a change in the algorithm that seemed like it might not be the best idea for a sequential program would be a really good idea in terms of parallelism. And that was the idea of kind of doing a Merditch-style predictor and corrector type method. So we would predict what might collide in the future, run without doing a lot of collision detection, then look back at the trajectory, and if we got it wrong, go back and undo all that work, all right? And if we got it right, we continue. Well, that seems like a really bad idea, except that it makes your simulation embarrassingly parallel in the sense that if you're using an explicit time integrator and you're not doing collision detection, you can integrate different parts separately. So it allows us to exploit a lot of parallelism. So we've started to think about those lines in the context of structure. Brennan Smith and Danny Kaufman are right now looking at these billiard balls and oscillating boxes of pearls in the context of massive simulations of landslides using granular media. So taking these things but running them with 1 million or more grains. And there we have to question, the methods that we picked for solving, the quadratic programming or linear complementarity problems, maybe those are appealing when you have smaller problems. What's the right thing to do for larger problems while still maintaining these requirements? So we're grappling with these questions, but in general, I don't have answers.
More questions? Thanks again.
Thank you so much.